What's going on, everybody? It's Mr. Gustin. I'm back in the physics classroom. Today, we are still looking at simple harmonic motion, but we're looking at a new object that undergoes this simple harmonic motion. We've studied pendulum. We've studied factors that affect the period of a pendulum. Today, we are going to start studying springs, our second object that undergoes simple harmonic motion that we're going to look at. Okay? Today, we're going to conduct an experiment, two experiments really, to test two factors that might affect the period of a spring. So I've got a set of springs over here, different colored springs with different spring constants. I've got a set of masses over here, and essentially our setup is this, right? I'm going to have a spring. I'm going to hang a mass from that spring, and as you see, it's going to start to stretch that spring. Now, an oscillation for a spring looks something like this. And this is a stronger spring. Let me find a little bit of a weaker spring, a smaller spring constant. Now, an oscillation for a spring looks something like this. If it does separate, an oscillation would be the time, or the motion of it going down, up, down, right? Like it goes down, starts up, goes down, bounces up. That's one oscillation. So I'm thinking about how I can measure the number or the period. I'm measuring the time it takes to start from the top, go down, up, down, up, down, up. That would be considered the period, the time it takes to go from top to bottom back to its initial position. So that's what we're going to test. I'm going to test different factors that might affect that. So I've got various springs with various spring constants. I have various masses in the classroom as well. So we're going to think about if I wanted to test some factors, namely two big factors that I can initially think of is I've got different masses and I have different spring constants. I could probably test the effect of spring constant on period. How does the strength of the spring affect the period? And I could go ahead and test the effect of mass on the period, meaning if I kept one spring constant, how might that affect the oscillation frequency or period of that spring. So I've gone ahead and already made a data table for us as I thought about it. And I've got two, okay? I've got essentially two different experiments set up, but really it's just two different independent variables. I can go ahead and change my springs, use many springs with different spring constants and see how that impacts the period, kind of my independent variable and my dependent variable. And I also have, using one spring, how the masses that are hung from that spring might affect the period. Again, my independent and my dependent variable. My data tables are below. Essentially, I'm going to have the spring constants. I will measure the time it takes for 5 oscillations, maybe 3, maybe 10, whatever you want to do at home as you watch this video. But I'm going to measure time for 5 as a good number. Divide that by 5 to find the period of each oscillation, each scenario, each setup. So these are the two experiments we have. We're going to go back in the back of the classroom and take this data. It is your job to take this data, so make sure you're watching it in ×1 speed. Don't double speed me to speed through it. You got to watch it in real time to get appropriate time data. Once we have that, we can come back, graph this stuff, and figure out what is the equation we have from this data. Here we go. Setup number 1. I'm going to go ahead and just let you know right now that the box of springs comes with this nifty cover, and the cover has all the spring constants on it. So let's go ahead and add this to our list, and we're going to roll through them in order. We'll do the the smallest spring constant to the largest. So when I'm thinking about spring constants, it goes in increments of 5, I believe. We have a 25 Newton per meter spring, and then we have 30, and then we go 35, and then we go to 40, and then we don't go to 45, we actually go to 50 newtons per meter. And so we'll roll through these in order from weakest spring to strongest spring. And if I'm thinking about what variable might I need to hold constant while I change spring constant, if I'm not sure its effect on oscillation, it's going to be mass. So I'm going to want to hold the mass constant while I go ahead and do this experiment. So I'm going to pick up a mass that I think works well, and that's going to be a 500-gram mass, I think. I think that will work well for us as 500 grams to use. And I'm going to go ahead and hang this from this hook right here. It's totally in frame. And now the one thing I should not do is pull it down to initiate the oscillation. If I pull it down to initiate the oscillation, it in fact might slam itself into the spring and pop right off. That will ruin my data. So instead what I do is I go ahead and make sure that I lift it up until that mass in the spring kind of coils touch. And then I'll let it go from here. I'm thinking probably 5 oscillations for you at home. Time the whole thing. You might want to skip the first one, maybe 4 oscillations. No fewer than 4 oscillations at home. All right? So I'm going to let it go in 3, 2, 1, go. All right. That was more than 5 for sure. You have that data. I don't have that data, but you have that data. I'm going to keep using this same mass, but go from the red spring, which is 25 newton meters, to the blue spring, which is 30 newton meters, and we'll do the entire thing over again. All right. Blue spring's a little stronger, maybe less obvious oscillation. We'll lift it up, and we're going to let it go in 3, 2, 1, go. All right, again, you're measuring. If it starts at the top, one oscillation would be top, down, top. Or if you don't like starting it when I drop it, you can start at the bottom and do bottom, top, bottom as one oscillation. You pick. All right, that was the blue. After blue, we're going yellow, like Coldplay. Yellow, Chris Martin. Here we go. Yeah. Oh, you can actually feel it. It's actually stronger. I can feel it stronger. You can actually see its equilibrium position is getting closer and closer up to its actual natural length. So let's see what we got here. Ready? 3, 2, 1, go. Wow, that's a little bit harder to look at, right? That's a little bit harder. It's much faster, obviously, which is why it's a good thing we're doing more than one oscillation. After yellow, we go white. The white spring. Here's the white spring. Did I mess up the last one, folks? Did I use the wrong mass? Folks, I used the wrong mass! Shoot! Back to yellow. Back to yellow. Rewind. Try it again. No, I don't know. I think I used the wrong one. We'll try yellow again. Go. Ooh, why is it wobbling so much? All right. Hopefully that's enough for yellow. Now we got white spring. White spring should be at 40 newton meters. 40 newton meters to the white spring. 3, 2, 1, go. This white spring looks different than the yellow one. We'll try it again. All right, we'll see how that works. Maybe that white spring did look a little different. And lastly, our strongest spring is green. We'll hang this from here, and we'll give this one a shot. It starts to wiggle a little bit. I'm not sure why it wiggles. It could be because the mass is bent. One more time. And then it starts to wiggle. That's too much. Okay, so now we've tested, right? We have tested the effect of spring constant. We have our spring constant data over here. I will let you go ahead and analyze that data, graph that. We'll come back to this later. Our next test was to go ahead and test the effect of mass on period of a spring. I'm going to go ahead and use the weakest spring we have. That way mass will impact the most. Otherwise, I'm using a real strong spring. I'm going to have to use giant masses just to displace it from equilibrium, and I want to get a wide range of numbers. So I'm going to go ahead and use my red spring, which is the weakest of the springs. That way, and then vary the masses on it. Okay, so we'll start with like, let's see if a 100 gram mass will even separate this thing at all. No, 100 grams is not going to do it. Maybe a 200 gram mass will do it. Ooh, that's hard to even see. So 200 grams is not going to cut it. So we'll start with probably maybe 300. 300 gram mass. We're going to have to add masses together. 300 gram mass will definitely see some oscillation there. Yeah, we're going to start with that. All right? So we're going to spread this thing out. We're going to try to go in some increments here. Let's go ahead and get at least 5 data points on our graph. We're going to go mass of 300. We'll also go 400 grams. We'll go 500 grams. Then we'll go 750 grams. Then we'll go 1 kilogram. I guess we should probably do this, huh? Make these all kilograms. And we'll end up going like let's make it 1.5 kilograms. Let's really spread this thing out over a wide range to get some good data. We want those periods to be very different so we can get a wide spread of data. If those data points are too close, any minute errors will cause major impact in our analysis. So 3, 4, 5, 750, 1 kilogram, and 1.5 kilograms, okay? So here we go. I've got it set up right now with 300 grams on there. Let's go ahead and just place it upward. 3, 2, 1, go. All right, that was 300. Let's go ahead and go to 400. Same mass is on there, 400. All right, I said after that we're going to 500, or half a kilogram, 500. All right, that was 500. We're going to go ahead and add 200 to make it 700. And then, heck, we'll go ahead and add a 50 gram mass, make it 750. All right, 0.75. You can see the spring really starting to stretch now. We'll get this thing up, ready, and go. Okay, that was 750. Now we're going to 1 kilogram. 1 kilogram mass. It's going to really start to stretch this thing out. Whoa, way down here. Ready? Go. All right, after 1 kilogram, we got to add that 500 back on there. Let's see if it's going to work. Will it work, or is it going to touch the ground? Oh no, it touches the ground. We have to make an adjustment. Let's go 1.2. Let's go 1.2 kilograms instead of 1.5. 1.2. And we'll go ahead and make its oscillations a little bit smaller. Can you still see it? Oh, you can't hardly even see it. All right, so hopefully you can obviously notice and see the changes in period, but I wonder what they are graphically. I wonder when I do graph them, what ends up happening. So you take your time, you analyze that data, you figure out the period, not just the time. So based on the number of oscillations you did for your data, that will dictate your period, okay? So if you did 5 oscillations divided by 5, you did 3 oscillations divided by 3, but I said no less than 4, so make sure it's no less than 4. Now, that being said, what I end up with when I do this experiment, when I do it, here is what I end up with. I end up with the spring constant looking like this. My data for the spring constant looks like this. My data for the mass ends up looking like this. These are two very different functions. Make sure you can see this one. Kind of went away. Now, off the bat, you might think initially, spring constant is an inverse relationship only. You need to analyze this more. When I actually analyze this more, I find it's not just an inverse graph. Now, the period and mass graph looks like a square root graph because it is a square root graph. So when I end up graphing this, what I find mathematically is that this is related to the square root of mass, okay? What I end up finding over here is that period is not just related to the inverse of the spring constant, but it's related to the inverse square root of the spring constant. This is what I find. And so when I start making an equation or a giant proportionality statement, I end up with this. The period is related to both the mass and the spring constant. So we can start thinking about this. As the spring constant goes up, period goes down, and that should make sense. If the spring constant goes up, the spring is stronger. If the spring is stronger, the period is going to be much shorter. On the flip side, if the mass of the object increases, it's going to make the period longer. And again, that should make sense. The spring applies a force, a spring force, a linear restoring force. The heavier the object, the more inertia. The harder it is, or the slower the acceleration is going to be. Therefore, the period is going to take longer. It will take longer for an object to oscillate back and forth when it experiences the same force as something much lighter. That's what this data is starting to show us. So this equation is on your equation sheet. This is the data that supports the equation. Now again, this is a simply harmonically oscillating object. So we see that there is some kind of repetition or repeating motion with this. So you actually see what is the slope of this thing. It's actually 2 pi, similar to our trig functions, right? Like there is this oscillatory or repeating motion here. So this equation is not just period equals square root of m over k, but there is a 2 pi component to it as well to indicate the repeating nature of this thing. That's where our graphs come from, and that's how it compensates for this repeating oscillatory motion, just through that 2 pi term. Your job now is to go ahead and answer some analysis questions around this, but make sure you have these graphs, make sure you've done this analysis, make sure your data matches my data. And if it doesn't, you ask me in the comments, you send me an email, or you ask me in class, okay? Until next time, see ya!